Well, welcome back, everyone. So we're going to start with the astrophysics session now with one of our own, Alex Gagliano. So he's an IAIFI fellow, splitting his time between MIT and Harvard, so at least we know he's half good. And he works on loads of things that are time domain in astrophysics, in particular things that go kaboom, so it should be a fun talk. Thanks, Alex.
Thanks very much, Carol, for that half-good introduction. I am Alex Gagliano. I'm going to be talking about time domain astrophysics. I should caveat that this is a realization, a single realization, over the distribution of possible talks conditioned on my own science interests, so it will be very heavily focused on representation learning for supernova science specifically. Okay, I study supernovae, the explosive deaths of massive stars greater than about 8 solar masses. We can observe these incredibly energetic explosions out to vast cosmic distances. And this is essentially what it looks like. We get a full-frame image of a field, a patch of sky, and from out of nowhere, a single pixel lights up. Maybe a couple of pixels if you've saturated the pixel, the CCD. But from this single pixel, we are meant to infer all of the properties of the star that lived and the explosion that took place. And so supernovae are very interesting scientifically because they ride at this interface between the final stages of stellar evolution, which are very poorly understood, and the initial stages of a compact remnant. There are many, many science questions that one can ask along every position along this forward model from progenitor star to compact remnant. And across decades of dedicated scientific studies, we still do not understand very well this process or, again, any individual point. And to make things even worse, of course, for the vast majority of systems, this is not what we observe. This is what we observe. We observe predominantly just the supernova, just these couple of pixels of light over time, and from it, we're meant to infer this entire history. And so, just to kind of ground us in what the observations look like, here's a supernovae that we've observed very recently. There's a press release coming out on Wednesday about it, so keep an eye out for that. This is a supernova called 2023 ZKD. And for the vast majority of explosions based on a single energy source, that pixel, over time, gets brighter and it gets dimmer. And we can describe that by what's called a light curve, just a curve of the light changing in brightness over time. For the vast majority of explosions, this light curve goes up, it goes down, the event is gone, it's over. You have your compact remnant. This supernova didn't do that. It was very interesting. We were monitoring it, it went up, passed behind the sun, so there's a massive gap in the data right at peak, of course. It got dimmer, and then it started getting brighter again. And that signaled to us that something very unusual was happening. You could tell that these observations are irregularly sampled, they're very messy, there are massive gaps. In this particular event, we also found in a rare example that the star that this explosion came from had been steadily brightening for years leading up to the explosion. So this is one rare case where we actually can connect the pre-explosion and post-explosion phases of this system. We can also measure the properties of the explosion as a function of wavelength over time. We gather what are called spectra, and these tell us a little bit more about the physical characteristics of the explosion, the energetics, the chemical composition. The combination of these two modalities is what we use to reconstruct all of the underlying physics of what's going on. And we can parameterize this by saying the following. Essentially, I want to model a posterior for a given set of physics conditioned on the fact that I've observed a set of data. Right? This is a very common scenario across all of science, but specifically for supernova science, you get brightness over time, you get spectra, which are a function of wavelength, and for all of the different science questions I want to ask, you have to condition that probability on the data that you've actually observed. And there are reasons why in practice, calculating this analytically might be very, very difficult or completely intractable. One of the reasons is potentially you don't have a good forward model that describes your observations. You don't know how to go from the underlying physics toward the set of observables that we typically collect. And either that's too computationally expensive or you just don't believe it, so you can't calculate this likelihood at all. I will caveat that this is not primarily my area of research, so I'm going to move on. But I will just mention that there's been a lot of work to either constrain the likelihood or to circumvent it completely using, for example, flow-based techniques. Another problem that you can run into is that you don't really know what data that you collect are most predictive of your physics. And this is the domain of representation learning. You want to gather some higher level semantic features from the data that you collect that might be descriptive of the physics that you're trying to describe. You don't want to parameterize every pixel. In the vast majority of cases, that's either computationally inefficient or just prohibits the solving of the problem entirely. So for supernova science, typically we group supernovae into different classes based on their observational properties. And there's been a whole suite of literature of handcrafted features that describe either the light curve on the left or the spectrum on the right of a supernova to better categorize them. On the left, there are some properties that we tend to use to measure the properties of the light curve, like the rise time, the color, the change in brightness across different filters. But you can imagine that just taking a couple of those features really compresses the rich information about each supernova and what makes it interesting, how the physics are perhaps just slightly distinct from the base class, and collapses them into just a few numbers that are not very expressive at all. And on the right, the situation for spectra is often much worse. A lot of times we simply describe the spectrum by one number, which is its distance to the closest matching template from the literature. That's how we describe that spectrum. You can imagine there's a lot of rich information in this data that we want to be better about capturing. And so as we've moved beyond hand-engineered feature extraction methods, we've moved toward classification solely based on machine learning techniques. So this is now a cottage industry. There are many different classifiers that are built up solely around taking the raw observations and going to the underlying class, circumventing the need for hand-engineering features. There are many that come out every year. I've been a part of a couple of them. But there's a problem with this cottage industry at present. And that is that the models that we've built, we've seen time and time again that they're extremely brittle. They completely fall apart in the face of subtle distributional shifts from training to observed data. They don't work across different surveys. We really think that we're not learning the right features from our data that tell us something fundamental about these explosions. We're just extracting the features that are useful for solving that particular training task, which is not really what we want to do. And so now we are moving toward finding better features through self-supervised pre-training objectives. Many state-of-the-art methods across other disciplines will typically start with some self-supervised training task with the intention of teaching the model something about the underlying structure of the data that we're giving to it. And then, in a second fine-tuning stage, we will teach it about the specific downstream task that we really care about. And the hope is that because you've trained a lot of your weights based on this initial self-supervised pre-training task, you're now better able to perform with minimal fine-tuning across lots of different data sets. And there are many different objectives that people are exploring right now for this self-supervised pre-training. I should mention this is a very active field of research, and things are improving all the time. I was chatting with a graduate student at MIT that I'm working closely with, and we came across this paper from computer vision. And this paper argued that potentially the features that you extract from your data for reconstruction are not necessarily the most semantically meaningful features that you want to extract from your data. And so you can imagine, here's kind of a toy example. If you're trying to encode images of faces, the specific realization of that face, this woman and every strand of hair and where it falls, how the lighting bounces off her face, is not necessarily relevant to understanding the intrinsic properties of that person, her hair color, how tall she is. And you can imagine that what we instead would like to do is kind of offset all of those stochastic high-frequency features to a separate piece of the reconstruction process. And so that's what we've been working on over the past couple of months. So in this, what's called a diffusion autoencoder, in this paper in 2021, they argued that you can take a basic encoder for the image, you can learn a smaller dimensional representation of that image, and then you can condition a diffusion model to decode into a realization, a reconstruction of that image, conditioned on both a noise map and the features you've extracted in stage 1. So they argue that when you do this, this latent representation is somewhat agnostic to the high-frequency features in that image. You still get very good realizations, but now your semantic features here map to intrinsic underlying properties of that image. And so here they give an example where you can map it to properties based on a small labeled set of data, like is the person smiling, and you can tweak those semantic features, pass that into the reconstruction, and warp the data in a way that is meaningful, in a way that we really care about. We were really curious about this, and so we decided to co-opt it and tweak the architecture somewhat. And the initial task that we explored was galaxy reconstruction. So supernovae happen in host galaxies. There are correlations with those host galaxies. And in this case, we took a very similar architecture to encode multi-band galaxy images into a latent space, semantically meaningful latent space. And then we condition a diffusion model based on that set of latent features and a noise map to reconstruct into hopefully realistic realizations. And we found that a model like this is very, very expressive. So here, one of the models that I've been working on compresses 72 by 72 by 3 images, so what is that, 1,500 pixels of data into 5 numbers, and gives you back these reconstructions. And these are, again, realizations of a potential image conditioned on that latent vector of 5 numbers. And the nice thing about really, really bottlenecking this latent space is that now we can look at connections to underlying physical properties of those systems and their connection to the latent features. So on the bottom, we can see that there's a very strong correlation between physical properties like stellar mass, star formation rate, redshift, and some of those latent dimensions. This is not t-SNE or UMAP. These are real dimensions that it's learning. These are the real parameters. And of course, because it's a probabilistic decoder, we can also draw different realizations and get some sense about the things that the model cares about and the things that it doesn't. In this case, you can see that it doesn't really care about things on the periphery of a galaxy, like neighboring stars, for example. We can go one step further and take those 5 numbers and train a very simple lightweight model to predict physical properties out from those multiband images. So you can see that here we're predicting the mass of the galaxy, here we're predicting the redshift of the galaxy, and we perform very well just based on those 5 numbers. But again, because this is image-based, we can also go one step further and start to say, what are the morphological properties of a given galaxy? And so here, again, with those 5 numbers, we've trained a binary classifier to go from that latent vector to different morphological properties from a small labeled data set from citizen scientists. And we can say with decent accuracy that a galaxy is a merging galaxy, that it has spiral arms or not, that it's edge on or face on. And so you can see that just 5 numbers can adequately capture both morphological and physical information about these galaxies. And we're now exploring the value of these 5 numbers for host galaxy studies of supernovae. You can see here for similarity searches, both the physical properties and the observational properties really matter of a galaxy. And that same architecture, we're now exploring it in many other domains. Here's just some very preliminary work showing that we can adequately reconstruct supernova light curves here with a latent dimension of 10. This is the residual set of plots on the bottom. And there's a student, a very excellent student, Alison Ito at MIT, who is exploring the same architecture, applying it to Galah spectra of variable stars. And it seems to perform very well out of the box. So we're really excited about this. I talked a little bit about self-supervised learning, but of course, the way that we construct a space doesn't necessarily need to be unsupervised. A lot of times we want to build a latent space based on physical properties of the data that we collect. And so together with Carol Cuesta, who's another IAIFI fellow, and Edgar Vidal, who's an excellent student at Tufts, we wanted to ask, well, what if we just set as the pre-training objective learning the physical parameters directly? So we started with simulated data, and there are certain parameters of a forward model that describe how a supernova evolves in time. This is, again, its light curve. It gets brighter, it gets dimmer. And we can constrain, using a simulation-based inference network, the physical properties of the simulated supernovae. And then we can also tack on a categorical network. So what we've done here is constructed a two-stage approach. The first stage is where the network predicts what energy sources are powering this explosion from among a set of 7 combinations. And from there, it predicts the physical properties of the explosion under the assumption that it is powered by that particular combination of energy sources. And so here are some very early results. We're finding that when you build a model in this way, we structure a latent space of encoding light curves that preserves physical information and is really useful for learning the connection, the intrinsic connection, between some of the explosions that we observe. You can see here, for example, that there's overlap in the latent space, here projected down into 2 dimensions, based on whether an event is powered by interaction with surrounding material, radioactive decay of material. You can see these supernovae are powered by multiple energy sources, and so there's greater degeneracy in the latent space that describes that. And we're hoping that this will be a really useful tool for data exploration of light curves in upcoming time domain surveys. Another problem that we can run into is that a lot of times the data that we collect are multimodal, and we don't really know how to combine them in a way that's meaningful. There has been a revolution in the development of multimodal models. Part of that was heralded by the push toward multimodal LLMs. These are language models that have then been trained natively to incorporate information of images, for example, vision language models or VLMs. And one of the major breakthroughs in training a model for this particular type of multimodal inference is called CLIP. So they basically said, I have a set of labels, I have a set of images, and I want to embed them both in a shared latent space where the thing that I really care about is the distance between an image and its corresponding caption, corresponding label. And I'm going to train the model to push those embeddings close together. And if I have an image and I compare it to a caption that's not associated with that image, I want it to be far in the latent space. And so they found, with just 60 hours of video and some painstaking labeling from a research team at NYU, that you could learn semantically meaningful concepts in the latent space from the images directly, from the frame by frame of the 60 hours of video. So they argue that this is a really meaningful way to structure a latent space such that you're able to incorporate the 2 modalities of information. This type of training has been co-opted and used across several different domains in astrophysics. I'm highlighting here where we threw our hat in the ring in 2024. MAVEN was a multimodal architecture that developed out of an IAIFI hackathon. It was really fun. Some excellent students worked on that. In this particular example, Liam Parker and company trained a contrastively learned latent space based on a series of galaxy images, their associated spectra, to align in the latent space. And they argued that when you do that, then out of the box, you gain substantial improvements in performance across several downstream tasks. But we had learned, after developing MAVEN, that contrastive-based methods like CLIP were very good at semantic coherence across modalities. They preserve shared information between the modalities, but they're not great at preserving the information that is distinct and potentially may be very relevant for the physics that you're interested in exploring downstream. And so, together with my student Yunyi Shen, we're exploring a series of slightly different architectures and training objectives in order to combine multimodal information without losing the semantically meaningful, distinct information in each modality. And so the particular task that we're exploring right now is you have a series of supernova light curves, you have spectra for only a few of them, and for the rest of them, you want to infer what the spectrum is that you didn't observe. And so we're training a model to do this. It's a basic autoencoder, but the latent space is trained to be a mixture of experts, basically the sum of distributions that correspond to each modality of data that you're passing in. And so what we're learning is that when you train in that way, we get very high quality reconstructions of any modality. It accommodates missing information, so you can choose at inference time whether you care about reconstructing a light curve or whether you reconstruct a spectrum instead, and that you don't have the same degradation in performance at inference time as you did for some of these contrastive methods. And we're exploring ablation studies right now that are finding that the reconstructions are stable and accurate when additional photometry is masked. Basically, as you reduce the quality of the light curves that you pass in, you're still able to get out a reasonable spectrum. And Wendy, a student I'm working with, is now co-opting this to retrain it for multiple supernova classes and apply it to real data. So this is a slight turn, but I wanted to take the opportunity to discuss very briefly 3 topics that I think will really revolutionize in the next decade machine learning for time domain astrophysics. I'm very excited about these. The first one is not machine learning. The first one is a set of forward models that describe how a supernova evolves. You can imagine that a star evolves across many billions of years, and then in a fraction of a second, it explodes. And the behavior in that fraction of a second determines the evolution of the explosion across months and potentially years. And these dramatically different timescales of evolution make this a really difficult thing to forward model. And luckily, we're getting better. We now think that the explosion might require 3 dimensions. We initially did things in 1 dimension. We found that things weren't exploding in the way that we really wanted them to. And so now, by stitching together different simulation codes operating along dramatically different time scales, we're now very close to actually being able to predict some of the light curves, spectra, the observational properties of different explosions from first principles. I'm very excited about this, and I think it'll open the door to a broad range of machine learning-driven techniques to infer physical properties directly from the observations we collect. The opening slide that I had was an image shown in the first data release of the Vera Rubin Observatory. Vera Rubin Observatory later this year will begin its legacy survey of space and time. It'll operate for 10 years, and it'll discover 1 million supernovae per year. This will break exponential scaling beyond the discovery rates that we've seen so far. We're very excited about it. But the light curves that it will collect per supernovae are slightly different from the light curves that we've ever seen before. And so to really bring that point home, on the left, I'm showing a mall-wide projection of the night sky, and at 4 different points, I'm tracing out the number of observations across a few years that Rubin will collect. So if I play this forward, you can see that based on the particular properties of the legacy survey of space and time, there are massive gaps in the set of observations. There are high seasons and low seasons, and the observations are specific to the position in the night sky that a supernova occurred in. Of course, that has nothing to do with the underlying properties of the explosion, but it will matter a lot for our ability to extract meaningful physics from those light curves. And so something I've been thinking a lot about lately is the question of, if you have many, many low-quality light curves, can you say something through potentially hierarchical modeling about different classes of supernovae? Can you make stronger constraints by assuming that they're drawn from a similar distribution of physics? This is something I'm really interested in exploring in the future. If you are as well, I would love to chat. And the last point that I wanted to mention is machine learning-driven survey optimization. There was a lovely talk earlier by Amy. It talked about reinforcement learning. There have been a few attempts to use reinforcement learning to guide us toward taking observations in time of different explosions such that we maximize some cumulative reward. We're looking at the night sky. These things evolve very quickly, so we have to triage what we look at and what we ignore. That's a very time-sensitive game, and it's really hard to parameterize our science interests into one single scalar quantity. And so there have been a couple of attempts to automate telescope follow-up of time domain phenomena based on reinforcement learning frameworks. And you can see in this example here is random follow-up, random guessing. Here is the performance of the reinforcement learning framework. Here are humans who are not particularly specialized for that task, and here are human-level experts at the particular way to parameterize that science score. And you can see that to within one standard deviation, we're not able to do this right now better than random. This is something that I think is so exciting, and if we're able to figure out a way to describe the type of follow-up that we want to do, we can take better advantage of the telescope resources that we have to make better discoveries. This is something that I think is very low-hanging fruit and is going to continue to come up in the years to come. And I will stop there and maybe just say, to reiterate, supernovae encode the final stages of stellar evolution, the initial stages of a compact remnant. So they're this very interesting transition point that connect many different areas of physics. The data that we collect are very unique and require custom architectures, custom learning objectives to really extract as much physics, as much semantically meaningful information as we can from them. And I'm excited for new upcoming surveys because I think they will only increase the potential that we will be able to take advantage of these automated techniques to discover new phenomena. Thanks very much.
Thank you, Alex, for the really fun talk. So we have 15 minutes for questions.
Thank you for the very nice talk. I had a question on your generative decoder.
Yeah.
So I agree with you that theoretically, that's the right objective, to try to force the representation to be maximally informative about the image. Mm-hmm. But I'm curious if you try to see what happens against a simple decoder trained with an L2 loss. And if you've compared the amount of information you recover at the bottleneck.
Yeah, so I will say that this particular task of reconstructing galaxy images with a compact latent space is something that I've been exploring for maybe a year and a half right now through various techniques. So I have done extensive benchmarking. And I will say that the traditional autoencoder and decoder architectures that you can just use off the shelf, trained with something like an L2 loss, like you're describing, they just reconstruct smoothed.
Oh yeah. But if you take the mean and the average of the one that you sample, is it any better than the smooth one that you decode?
That's a good question. Yeah. I don't think I've drawn from it in the way that you're describing.
I don't think it's that different. I'm curious to chat more.
Cool. Yeah, I would love to chat.
On this project as well, I wanted to ask. So in the previous slide, when you show the image of the person, mm-hmm. It's, from what I understand, you're distinguishing the noise from the essential features of the image. And in this case, it really looks like that noise is noise. When it comes to the galaxies, maybe you're showing it, but could you clarify what does the noise look like, the equivalent of this noise image?
Sure. So this is conditional diffusion starting from a noise map. So
I see. You're not pulling the noise
out. That's exactly right. Yeah.
I see.
So when we co-opt that architecture, we just start from random Gaussian noise.
I see.
And then use it to go to these images.
Okay.
Hi. Thanks for your presentation. One question I had is about the compact latent space. Mm-hmm. The disentanglement, literature, it suggests that there exists some generative factors that are not easily embedded in few dimensions. Have you seen any particular physical properties in your specific domain that are not easily embedded in a few dimensions?
Yeah, that's a great question. This is one of the reasons why we were applying it to many different domains, is we were trying to see where it breaks down, what exactly can't it reconstruct, and we're struggling right now. So if you have ideas about what it might struggle to preserve, I would love to hear them.
Sure. Yeah, I can talk with you after.
Yeah,
this.
great. Thanks.
Here, so when you were talking about contrastive learning, and you said that you found that the latents that were encoded were best at finding things similar rather than distinct in the data. Can you talk about what probes you used to come to that conclusion?
Totally, yeah. So I don't think I have a Maven slide, but in the Maven architecture, we were combining supernova light curves and spectra and then using them for specific downstream tasks and comparing the performance to what you would get if you just encoded spectra, if you just encoded light curves. And we were hoping that potentially there was some semantically meaningful information from the spectra that it was pulling out to improve performance over the baseline, which was light curve only. And we found that that wasn't the case. Basically, it brought them to a shared latent space where the lower quality representation reigned supreme. And so we got comparable performance, but it didn't blow it out of the water, which was what we were hoping for. Yeah.
Hi. Thanks. Great talk. I had a question, I guess, sort of related to this, is if you could talk about if you were concerned at all about like degeneracy in your latent space. I can imagine in the clip case scenario if you have semantic meaning that is degenerate. But in the case of your light curves, especially if you were discussing these gaps, maybe like you could have a light curve with a sufficiently large gap that basically makes it degenerate with something else in your latent space, if that's a concern.
Totally. How do I want to answer this? So I will say that there was a fair bit of trial and error just for us to decide on this specific design implementation that 5 was sufficient to capture these galaxy images. Of course, we have not encoded explicitly some kind of like factorized latent space such that we ensure that each latent dimension is like sufficient and distinct from all of the rest. And so I think that would require additional tweaking. For the case of supernova light curves, I think we have just asked the question of how compressed can we go such that it reconstructs sufficiently and it is not hugely sensitive to the noise properties of the particular realization, like a large gap in the data, for example. Yeah.
Thank you.
Hi, Alice. Yeah, very nice talk and very similar to what we're trying to do in particle physics. I was curious, so you kind of showed the kind of autoencoder thing and then you showed the latent space and you kind of motivated its working by showing kind of these kind of physics-informed quantities, which means that you have the labels and you could have just done supervised learning and kind of chopped it off the head and then use whatever latent representation that supervised pre-training would give you. So do you have a sense of what the relationship is between self-supervised pre-training and kind of, you know, physics-informed pre-training? And I mean, you know, if your benchmark whether or not things are working are these quantities, I mean, yeah, so I guess you could have also pre-trained in a supervised space. So
Totally. Maybe there's a distinction to be made between what the model sees in the way of validation versus how we establish as a proof of concept that this architecture is able to pull out meaningful information. So, of course, it's a diffusion model. All we're really learning is the score. It's unsupervised. I don't have a good sense for if you have a fully supervised pre-training objective versus an approach like this for the same bottleneck latent space, how performance might differ downstream. I think that would be interesting to explore.
I mean, I guess the thing that we're all after is like, can it find like some semantically meaningful feature that we don't know, right? But that's exactly the hard question. Like, how would you somehow get a model to learn that without, you know, kind of being sensitive to some pixel variations or something?
Yeah, and it's maybe a chicken and an egg problem because you can see that it picked out meaningful morphological information based on a very small labeled subset of the data. Of course, we don't have these labels for the vast majority of the galaxies, but if we're trying to validate that it's learning something meaningful about the structure of these galaxies, then you have to go off of the labeled information, right?
Thanks for the nice talk. I was just wondering about your slide about like population level estimates. Like, how would the selection function challenge be addressed in this case?
The selection function challenge.
Like, I mean, yeah, you need to accurately quantify the selection function of your survey to get these population level estimates. Like, do you have an idea?
It's a good question. In principle, we have simulations of LSST cadence, right? And you see it right here. They regularly release it. So we understand what's being observed when. There are rates that are continually being updated that describe these supernovae themselves. But I think there it becomes a question of how strong are the assumptions that you make ahead of time and what inferences can you make from your model downstream. If you make very strong assumptions about the intrinsic population of your supernovae, then in my mind it somewhat restricts being able to discover, for example, deviations in your expected rate at high redshift, for example. Yeah.
Thanks.
Yeah, let's thank Alex again.